Hey there! In this lecture, we're going to talk about data visualization. This concept deals with the techniques and tools that are deployed whenever we're visualizing the data. I think this is the most important asset for any data scientist, especially because after he has done his research, after he has performed operations on the data, he needs to present his findings in a presentation to his boss or anyone else. So rather than writing those things down or showing them on paper in words, it's always better, appreciated, and way more attractive if we can visualize our results in the form of pie charts, histograms, bar plots, and different techniques that we're going to see in a couple of minutes. So we've seen the types of data before. Now we're going to see the types of visualization that we're going to use for different types of data. Types of data visualization. So let's look at the different types of data visualization. Basically, the data visualization is divided into two types. One is for univariate visualization and the second is for multivariate visualization. You see, the fact over here is that we're dividing the different types of variables. Mainly, we're dividing variables into two types, univariate and multivariate. And we're going to use different visualization techniques for each of them. Univariate, we're talking about one variable, and in multivariate, we're talking about different variables. So let's talk about univariate visualization. One of the types of univariate variables are the numerical features. So you must be wondering, why are we using the name features over here? Features is more of a machine learning term and is used to represent data columns in a data set. So for the sake of this particular lecture, we're going to use the terms feature and consider that it is the same as variables. So in univariate visualization, we have numerical features and we have categorical features. And in multivariate visualization, we have three types of different ways to represent or plot two variables at a time. So as the name suggests, we are going to visualize two different variables and to understand the relationship between them. So first of all, we're going to visualize numerical against numerical and numerical against categorical and categorical against categorical. So we're going to take two variables and they're going to all be of the same type and different types as well. And since we're dealing with numerical and categorical data types, we're going to see the type of visualizations we're going to use when we are visualizing them independently or together. So let's see univariate visualization of numerical features. So we can further divide numerical features into two types, discrete and continuous. We've seen this before. So now we're going to see how or which type of techniques we're going to use. In univariate visualization, we're going to exclusively visualize one feature with numerical values. We're going to take one feature from the dataset and we're going to visualize it. So we know that the numerical features are of two types. The numerical values can be discrete or continuous. And we're going to see which type of plots and which techniques we're going to use with each of the type of numerical features. So let's look at the type of plots we have for visualizing numerical features. First of all, we have frequency table and histograms. Obviously, you've seen histograms and frequency tables before in high school or any other platform when you've studied mathematics on the basic level, or even you must have seen these types of visualizations, the type histograms on different videos or any other platform, or even on Google. Whenever you're studying statistics, data, this is the most common type of plots and visualization techniques we have. Secondly, we have density plots. This is somewhat not most commonly used and it is different from the popular plots we have, but let me assure you that it holds great value and is very important for representing, for visualizing and numerical features. Secondly, we have density plots. Density plots are not most common or popular, but they are very important whenever we are visualizing numerical features. And thirdly, we have box plots. This type of plots, as we will see later on, that these type of plots provide us with the most information we can extract from one feature. So they are extremely useful for a data scientist whenever he wants to extract more information about data or represent that information visually. So let's talk about frequency table. Frequency table isn't a type of visualization. It is basically a strategy, a technique in which we use to summarize data. So it's important for you to remember that we are using frequency table to summarize the numerical data. So numerical data is of two types, continuous and discrete. For now, we're talking about continuous data set. Let's consider continuous data set. So we know for a fact that continuous dataset cannot be represented exclusively or independently. So let's imagine this. You have a class full of students and you want to calculate or record the height of each student. After recording all the heights, you come to a conclusion that there are many students in your class that who have heights which lie in a particular interval. So if, for example, if we're talking about 100 to 200 centimeters and you realize that there are at least 6 students who have heights in this range. So considering that fact, we're going to group the heights of those particular students into equal lengths of intervals. So the number of intervals. So how do you decide for the number of intervals? Obviously, this decision varies from problem to problem, considering the size of your class or any other sample dataset that you're using, and it will be decided according to your problem. And the interval length is another issue that depends on the type of problem you're using. Like the example I gave you earlier, that most of this, there are at least 6 students who have heights that lie in the interval of 100 to 200 centimeters. So the interval length of this example would be 100 centimeters, right? But obviously that can be different. Like you can have that interval can be bigger. For example, those students might have height ranging from 100 to 300 or 400. That entirely depends upon the data and the problem you're facing right now. So let's look at the interval length. So there must be a way, right? After you've collected the data, you have to decide for the interval length. So we need to use a certain formula to calculate that. So we're going to select the height of the tallest student, and we're going to subtract it with the height of the smallest student, and we're going to divide it by the number of intervals, which you will be arbitrarily deciding, but it should be, the number of intervals should be between the range of 5 and 20. So after you've done all those processing and you've gathered your data and you've grouped your data into, you've decided the number of intervals, you've decided the length of your intervals, and you have categorized it into these similar groups, and the frequency represents the number of students you have who have heights that lie into these particular intervals. So that's it. We have just summarized the data, and considering we have summarized the different heights of all the students in your class, and then we're going to visualize it using histogram. So histogram, we're going to use it to visualize the frequency table we have just created before. And on the x-axis, as you can see, we have a feature W1, which we will be representing as the feature you were recording. For example, it could be height, it could be any feature you want to visualize. So the frequency obviously represents the count of each data point that lies in the particular interval. Obviously, in this visualization, the values are small. But if you're using the example of heights from a classroom, then this range would be entirely different. But the idea is still the same. The idea is we're going to use different groups, and we're going to pick different students who have similar heights, or at least they have heights in a particular range, and we're going to visualize their counts. So we're going to visualize the number of students who have heights, and they lie into different ranges or groups in these categories. So this is called the table we have seen. There's another name for it. We call the frequency distribution table. So the frequency is distributed according to the height. So next, and we're going to study this distribution of one feature at a time. And later on, we're going to see how important it is to understand the different distributions they are. So for now, it's important to see. So after visualizing this particular feature, we will say that we are going to study the distribution of W1 feature. Okay, so we're going to plot it against the frequency, and we're going to study the distribution after looking at these plot. So we all know, we've seen that a histogram groups values into bins of equal range, just like the frequency distribution table we've done before. But obviously, when you're visualizing or using histogram directly in programming, as we will see later on in the course, you don't really have to create a frequency table. You just have to plot that feature. We're going to just feed that data into the histogram function, and it's just going to plot you this graph. So the question is, why do we use histograms? Why are histograms so important? As I said before, the shape of the histogram tells us about the type of distribution, and the type of distribution will ultimately give us way more information about that particular feature. So after visualizing the distribution, we're going to see the shape of the distribution, and then we're going to reason with it, then we're going to extract insight, and we're going to get more information about that particular feature. So these are the different types of data distributions we see over here. We have bimodal, comb, edge, peak, normal, skewed, uniform. Out of these 6 distributions, bimodal, normal, skewed, and uniform are the most important ones. Bimodal is quite simple. We have 2 peaks over here, which means that we have at least 2 types of categories in the dataset that have the highest frequency. The normal distribution, we have another detailed topic about it, so I won't go into detail right now, but it's for now just remember the shape of normal, skewed, and uniform. So the normal, it's quite balanced on both sides. It has a peak in the middle, and skewed, and in the skewed distribution there is a peak on the left hand side, and the peak can be either on the left hand side or on the right hand side. It's completely unrelated. It can be on both sides, but the thing is the peak will be on either the right or the left hand side. Uniform, there's no maximum peak. You can see that it is basically the average frequency or the height of each bar is basically somewhat same, uniform. So let's look at density plots. Density plots are also known as kernel density plots because we're basically using a kernel function that is entirely mathematics. I won't go into the depth, but it uses a particular function. We feed the data into that function and it gives us these outputs, which are represented on the y-axis called as density. So we feed the data. For this example, we have night price distribution of Airbnb apartments. So I feed the price into that function. That's called as function x. So we feed the price into function x, it gives us a density, and then we plot this information on this graph. So the kernel density estimate shows the probability density function of the variable. The probability density function, let me explain it to you like this. So over here, let's look at 100. The 100 price, let's call it $100. The $100 price has at least about 0.0085 density value, which would mean that out of a probability of 1, it is 0.085 probable that this value occurred in that feature, in that data set. So this is very useful, especially when we want to see. So this is somewhat similar to frequency. Instead of just using the count of the 100 price, for that we needed to group the data into equal intervals. So in the density plot, we're not doing that. We're not grouping the data, and we're just going to use each individual value, and we're going to feed it to the probability density function. It's going to tell us that how much probable it is for the $100 price to occur in this data set. It is also known as the smoothed version of a histogram, since we're not grouping values together into different groups. We're just using it directly, but the shape actually suggests is similar, as we will see now. It is better for visualizing distribution. As you can see the shape over here, if you can imagine that if I had a histogram of equal bars, we would have a highest peak over the values around 0 to 100. So instead of that, we are just using a smoothed line which represents this, but the distribution shape, the shape of the distribution, is somewhat same. So as I said earlier, the shape of the distribution that density plots represent is somewhat similar. That's why we have the same types for these distributions as just like histograms. We have bimodal, normal, skewed, and uniform, and they have the same features and characteristics just like the histogram distributions. So let's talk about box plots. So box plots are used to summarize the distribution of a feature. They provide us with a lot of information. For example, they give us the information regarding median of the set of values. They provide us the upper and lower quartile values. Then we can use these values to calculate the interquartile range. And last but not the least, it can also give us information about the potential outliers there are in the dataset. So the box plot looks like this. The median is represented by the line in this rectangular shaped box. So the line not exactly in the middle, but the line separating the big rectangular box into smaller boxes is basically the median. The 75th percentile is on the right hand side and the 25th percentile is on the left hand side. And the range between this 25th and the 75th percentile is called the interquartile range. So on the extreme left and right, you can see dots red dots, which are basically the potential outliers. And on the left hand side, these are the minimum values in the data, and on the right hand side these are the maximum value in the data. Okay, so we have seen univariate visualization of numerical features. We have seen the different plots we use, the different techniques we utilize. Now we're going to move on to univariate visualization of categorical features. So categorical features are basically categories which need to be studied independently. And these categories have fixed set of values. So if we're studying a categorical feature in a data set, it has a fixed number of values, which means that the number of categories in that feature has a fixed number. Each of these values assign an observation to a corresponding group known as a category, which reflects some qualitative property of this example. So imagine a set of features and it has 3 different categories. So let's put it this way. You have a group of workers and there are 3 different classes. We have workers who work in a factory, we have management, people from management, and then we have the executive team, the CEO, the CTO. So you can say that there are 3 different classes of workers belonging to a particular company. So the fixed set of values, which as I mentioned, would be there are 3 categories in this particular company of workers. There is another special case of categorical features in which there are only 2 possible categories. We call them as a binary variable. The category is either 1 or 0 or 2 or 3. So in a feature, if there are only 2 categories, we call it a binary feature or a binary variable. Ordered categorical values are called ordinal, and that's what we have studied before in the types of data types. And ordered categorical values are called ordinal, as we discussed this before when we were talking about the different types of data types, so I won't discuss it again. Let's move on to the different visualization techniques we're going to use to plot categorical features. Firstly, we have the frequency table again. The frequency table is so versatile, we can use it for numerical features and to summarize the data of categorical features. Frequency table is a very powerful tool. We have bar plot. This is somewhat similar to the histogram but has some differentiating characteristics which basically differentiates it from histogram. So let's talk about frequency table. We've seen before that in numerical data, we have to group the data into different categories, into different groups, and we count the data belonging to each of those categories or intervals. But when we're talking about categorical features, we don't really have to group them together because each class is a category itself. Each class is a group itself. So we just need to calculate the count of each category. And we're going to use the frequency table to calculate the count of each categorical variable. So this is an example of a survey conducted in a university. We asked different students about their degree and the types of degrees they've had. So as you can see, there are different categories over here. We have high school, bachelor's, MBA, master's, law, and PhD. These are categorical variables. The values are independent and exclusive from one another. We don't have to group them together. There is no range between them. It's pretty obvious if you have a good grip on the different types of data types. It becomes quite easy whenever we are visualizing it or summarizing the data using these tools. So let's talk about bar plot. Like I said earlier, it somehow is similar to the histogram, but it has some distinguishing characteristics. As you can see, there is a gap between all these bars. These bars are not continuous, and each bar represents the count of each category. So just like in histogram, we used histogram to visualize the frequency table, and the same way the bar plot is going to visualize the frequency table of categorical variables. Just like histogram visualizes the frequency table used to summarize the numerical features, bar plot is going to visualize the frequency table used to summarize the data of categorical features. It is basically a visualization of a frequency table, and the y-axis is the count, just like in histogram, and the x-axis represents the different classes, which can be numbers, strings, or booleans. Like I said, each class A, B, C, D, there is no continuity between them. They are independent, and that is represented by the gap between these bars. The class category of the A and B, C, D, E. So the number or the set of the different classes we have is basically 5, and each class has a particular frequency which is just visualized in this bar plot. Okay, so let's talk about multivariate visualization. In multivariate visualization, the idea or concept behind is that we need to study the relationship between two numerical features. And we're going to visualize them using different techniques, and we're going to plot them in one graph. So the type of plot will basically depend on the type of features. So we have studied the different techniques or plots which we will be using to visualize one feature that has a different data type. So for whenever that feature is a categorical feature, we use bar plot, frequency table, and whenever that feature is numerical in nature, we use histogram, density plot, or box plot. So what would be the type of plot which we would be using whenever we are comparing two numerical features? Would it be box plot? So it's pretty intuitive if someone has studied the idea, the different tools to visualize numerical features. So it's pretty intuitive that if both of the variables we're visualizing are numerical in nature, so we might be using the type of plots we have seen before, or maybe not. So let's look at these plots. So the first one is scatter plot. Okay, this is something new. We've never seen this before. So maybe the idea of using the same plots we've seen before is not so applicable over here. The second one is a correlation matrix, which is another new type of plot that we've not seen before. Let's talk about scatter plot. The name suggests that we are talking about data that is scattered. It's important to remember that we're still talking about numerical data. So this type of plot visualizes the two numerical data type features into Cartesian coordinates. So imagine we have an x and y coordinate, and we're going to plot each data point on that plot on the x and y axis. So it will look something like this. We are going to select a range, and we are going to represent both the numerical features as Cartesian coordinates, and we're going to plot them on this graph. And then you can see it's quite clustered, and it is spread out, and it is scattered throughout the class, hence the name scatter plot. The next one is correlation matrix. Let's look at this. So this is the figure represents correlation matrix. As the name suggests, we are actually studying the correlation between the two features. How much are they correlated? We will go into the statistical and mathematical depth of a correlation and what it represents, and how we can actually use these values to study and extract more information about the data. But for now, what we here are going to study is it represents the correlation. The values are positive and negative. The one is basically when we are studying the features belong to the same type. So this metric represents and tells us about the correlation. As far as the mathematics and the theory is concerned, we will discuss that in detail later on. But for now, it's important to understand what this metric is representing. On the y-axis, or you can say on the rows of this matrix represent the features in a data set. So we have different variables on the y-axis, and we have the same variables on the x-axis. So this correlation matrix will be studying the correlation between different features. It visualizes it, and the numbers are, as you can see on the matrix, on the rows we have a certain set of features, and on the x in the columns are also the same set of features. So we are actually visualizing each feature with the rest and itself also. So whenever we are going to study the value of that feature with itself, it will always be 1, which means that a feature has the maximum correlation with itself. So the one value which is on the diagonal, it will always represent if both the features we are studying, they will be the same. So in the rows we have p class, on the columns we will also have p class if the value and the value between them will be 1, which is the maximum. So why do we use correlation features? The main reason for this is we need to see how much correlation do the features have with the target variable. This is basically a machine learning concept, and it has more application in the feature engineering. So when we will discuss feature engineering in machine learning, we will revisit this topic and this matrix, and we will learn how this matrix can be used to understand the correlation and how we can use that in machine learning as well. One important thing I want to discuss is that over here, the feature P class is not a numerical feature. It is a categorical feature. It's basically a category.